All right, lesson 1.5 is the parent of functions. So we're going to be talking about parent functions here. So in this lesson, we'll create a library of functions that are the foundation of our course. You should be able to give a complete analysis for each of the parent functions that include as many of the following as possible: domain, range, roots, y-intercepts, increasing, decreasing behavior, symmetry, whether it's even or odd, boundedness, local extrema, horizontal asymptotes, vertical asymptotes, in behavior, and continuity. All right, so first it talks about symmetry here. And some of y'all had already figured this out. I noticed on your 1.3 assignment, y'all were doing this when it asked for symmetry instead of finding if it's symmetric to the x-axis, the y-axis, the origin, or the line y equals x. But if you notice that if it is an even function, then it's going to be symmetric to the y-axis. You see the y-axis splits this in half, and if you have the point xy on your graph, you're also going to have the point negative xy on your graph. An odd function is symmetric to the origin. That means if you're going to have the point xy on your graph, you're going to also have the point negative x negative y on your graph. This one's not quite so easy to see, but if you find a point or a piece of your graph, so I'm just going to use this piece, and you reflect it across the x-axis, and then you reflect it across the y-axis, it should lie on top of itself. Therefore, you can tell that it is odd. And then if it's symmetric to the x-axis, that's just not a function. If you take a vertical line, it doesn't pass our vertical line test. Not a function. All right, so let's talk about those parent functions then. So the first one we're going to talk about is our constant function. And that's f of x equals c. And so I'm going to pull this up so we can't quite see that, but I'm going to write f of x equals c up here. All right, so we don't know what the c value is. It's just some number, though. It's a constant. So if I needed to build a table for this one, if my f of x is equal to c, then I can pick different x values. And if I plug them into that c equation, well, there's no x to plug them in for, so we would just get whatever that c value is. All right, so I'm just going to draw a line here at some random c value. All right, so that's my C. So when I do that, now let's look at the domain. Does my graph keep going to the left? It does. Does it keep going to the right? It does. Therefore, my domain is negative infinity to infinity because there's no jumps, no holes, no gaps, nothing funny looking going on between those infinities. But your range, does it keep going down? It does not. Does it keep going up? It does not. It's only that one y value. So therefore our range is just whatever that constant is, whatever our c value is. Then talking about in behavior, the limit as x approaches negative infinity. So that means as our graph goes to the left, our y value is going to stay the same. It's just our c value. The limit as x approaches positive infinity. That's as we go to the right, that y value is going to stay the same as well. So f of x equals our c value. Intercepts, we don't have an x-intercept unless the graph is on y equals 0, and then which everything would be an x-intercept. So most of the time we're only going to have a y-intercept, and that's going to be at the point 0, c. And then some of the other things that we can talk about on this. So we talked about going through our list up at the top. We talked about domain and range. There's no roots. That's your x-intercepts. Y-intercepts. Does it increase, decrease? No, it's constant. Symmetry, it's even because it's symmetric to the y-axis. Let's see, boundedness doesn't apply. There's no local extrema. There's no asymptotes. We talked about the in behavior. Is it continuous? It is continuous because we can draw this without picking up our pen or pencil. So it is continuous. All right, then the second equation we're going to look at there is f of x equals x, the identity function. All right, so if I look at f of x equals x, if I want to make myself a table here, So I'm going to write it above it. So f of x equals x. So I'm going to pick some x values. Those are my favorite. I'll use them almost on every one. But remember, f of x is the same thing as y. So this graph says y equals x. So if x is negative 2, then so is y. And if x is negative 1, so is y. If x is 0, so is y. And so we'd see our other y values. We can finish out our table there. And so we could plot those points. And then we could play connect the dot to get our graph. All right, then we can look at our domain. Our graph keeps going to the left. It keeps going to the right. There's no gaps, no holes, no jumps, no funny looking stuff in between the infinities. So therefore it is negative infinity to infinity. Now our range, does my graph keep going down? It does. Does it keep going up? It does. Any funny looking stuff in between those infinities then? No. No jumps, no holes, no gaps. So our range is also negative infinity to infinity. The limit as x approaches negative infinity. So as our graph goes to the left, our y values are going down, so they're going down to negative infinity. The limit as x approaches positive infinity. So as our graph goes to the right here, we can see that our y values keep going up, so they're going up to positive infinity. We have an x-intercept at 0, 0, which is also our y-intercept. All right, so let's go through all the other stuff we have. So we talked about domain and range. We talked about the roots, which are the x-intercepts. The y-intercept, is it increasing, decreasing, or constant, and where? Well, it's increasing. It's increasing over the entire domain, so it's increasing from negative infinity to infinity because our graph is going up. Symmetry. Our function is odd because it's symmetric to the origin. It's unbounded. There's no bounded to it. No local extrema, no asymptotes. We talked about the end behavior with the limits. And is it continuous? It is continuous. Excuse me. All right, moving on. The reciprocal function, y f of x equals 1 over x. All right, so we can do the same thing. We can make ourselves a table. All right, and so let's see if we put 1 over negative 2, 1 over negative 1, 1 over 0 is undefined. That tells us there's a vertical asymptote there, remember. Can't have 0 on the bottom of the fraction. 1 over 1, and then 1 over 2. And so we can graph these. We said there's a vertical asymptote at 0. We're going to graph that vertical asymptote with a dashed line. Oops, sorry, graphed those wrong. Now, so our graph, when I play connect the dot, it's going to be shaped by that asymptote, and then it's going to go this way, and we'll talk about why it's shaped like that in a few minutes. Shaped by that asymptote, and then we're just going to make it go this way, and we'll talk about that in just a few minutes. So our domain, does our graph keep going to the left? It does. Does it keep going to the right? It does. But we have that vertical asymptote in the middle, right? So therefore, it can't be negative infinity to infinity. So we're going to have to break it up into the two parts. We've got a domain for the left part, which is negative infinity up to the 0 not included, union, and then the 0 that's not included up to positive infinity for the right part. Now, our range, before we do the range, I'm going to jump to other, because we need to figure out what's going on right there in the middle. Well, we said we had a vertical asymptote, remember, at x equals 0. Do we have a horizontal asymptote? And remember, we talked about that. We said we look for the largest exponent on the x. It's in the denominator. Remember, we used the little no for a shortcut. The O is a 0 because then the horizontal asymptote is at y equals 0. So we actually have a horizontal asymptote here as well. And so I wanted to do that before we do the range because that affects the range. Horizontal asymptote, remember, it's never, ever, ever, ever going to cross at the ends. So we can see that that far left and that far right side are never going to go over that line. So therefore, my range, it does keep going down, it does keep going up, but we've got that jump right there because we're never going to cross that line, so it cannot equal 0. So our range is going to start from the bottom and it's going to come up to 0 but not touch it, and then we're going to jump right over that 0 but not touch it and go up to positive infinity. So then when we look at the end behavior, the limit, as x goes towards negative infinity, we can see that on our graph, as we're going to the left, our y values are going up. They're getting closer and closer to that horizontal asymptote, but they're never going to cross it. So the limit is going to be the horizontal asymptote, which is 0. And then the limit as f of x goes toward, the limit as x goes towards infinity, the y values are going to do the same thing. They're going to come down. They're getting closer and closer to that 0, but they're never ever going to cross it, so f of x would equal 0. Intercepts, well, both of our x and our y-axis on this one, our parent function, is going to be asymptotes, so we're not going to cross them, so there's no x or y intercepts. And then under other, we already talked about the vertical and the horizontal asymptote. Let's see what else was on our list. We talked about domain, range, we talked about x-intercepts, which are roots, we talked about the y-intercepts, increasing and decreasing. Well, we can see that on the left part of our graph, it's going to be going down as we read it from left to right, so therefore it's decreasing. So we are decreasing from that negative infinity up to the 0, and then after the 0, we're still decreasing, but we list it separate because there's a break between them, from the 0, to the positive infinity. All right, we still have to list them separate though because at the 0, it's not doing either of them. All right, let's see what else did we have here. Symmetry, is it even, odd, or neither? This one is odd because it's symmetric to the origin. It's not bounded. It keeps going up and it keeps going down. No local extrema. We talked about the horizontal vertical asymptotes. We talked about end behavior. Is this continuous? It is not. So we're going to say it's discontinuous. I have to pick up my pen or my pencil to draw this graph. All right, keep going on then. Our next function is a quadratic function. So to draw the parent function, I'm just going to pick some x's and plug them in to solve for my y's. So I'm going to pick my negative 2 to positive 2. So when I do negative 2 squared, I get positive 4. Negative 1 squared is positive 1. 0 squared is 0. 1 squared is 1. And 2 squared is 4. And so we can graph those. So that's what my parent function will look like. And now let's talk about it. So the domain, does my graph keep going to the left? It does. Does it keep going to the right? It does. No gaps, no jumps, no holes, no funny looking stuff in between the infinities. So negative infinity to infinity. My range, does it keep going down? It does not. Does it keep going up? It does. So my range is going to start at that lowest y value. Well, my lowest y value is right here at the vertex, which is when y is 0, and it's going to go up to infinity. All right, so but the 0 is included. It's not an open circle, so therefore we put a bracket there. All right, the limit is x goes towards negative infinity. So as our graph is going to the left, we can see that the y values are going up. So it's going to go up to positive infinity. The limit as x goes towards positive infinity. So as we go to the right, we can see our y values are still going up. So therefore, f of x will equal positive infinity. Our intercepts, we have an x and y intercept, both of them at 0, 0. And then others. So I'm going to go back through our list that we had on the front. We talked about domain and range. We talked about the roots or x-intercepts, the y-intercepts, increasing or decreasing. Well, we can see the left part of our graph as we read it from left to right. This piece is going down, so we're decreasing. From negative infinity until that vertex, which is where x equals 0. And then after that, we start to increase. So we start increasing at 0, and we keep increasing as we're going to the right. So we're going to keep increasing all the way to positive infinity. Symmetry. So we can see that this function is even because it is symmetric to the y-axis. Okay, boundedness, this graph does not keep going down, so therefore it is bounded below. Let's see, no local extreme. Well, we do have a local extrema. We have a minimum, a local minimum, or relative minimum of 0 at x equals 0. We can also see, they didn't really ask on it, but this graph is concave up because it opens upwards. Let's see, in behavior, asymptotes, there's no asymptotes. The in behavior was the limit stuff we already talked about. And is this graph continuous? It is. So there is our parent function for the quadratic function. All right, and as we keep going on, whoops, we can look at the cubic function. I'm going to have to cut off the top there because I think I want the bottom part of the graph. All right, so the cubic function, just f of x equals x cubed. So when I go to graph this, I'm going to pick some x values. Again, I'm going to pick my -2 to +2. And I'm going to plug those in. So -2 cubed is -8. -1 cubed, -1. 0 cubed is 0. 1 cubed is 1. And 2 cubed is +8. And so we can graph those ordered pairs. Now I can't graph the -8 or the +8. So I'm just going to have to graph the other 3. But I wanted them in my table because I know that it's going to be way down there somewhere, correct? For the -8, and the 2 +8 is going to be way up here somewhere. So the point of that is it's going to increase and decrease really fast right there. So when I go to draw this, I know I'm going to have to go down steeply. And when I draw the other piece of it, I'm going to go up. So there's our cubic parent function. So domain, does it keep going to the left? Keeps going to the right. no gaps, holes, jumps, anything funny in between the infinities, so negative infinity to infinity. My range, it keeps going down, it keeps going up, nothing funny looking in the middle there, so therefore it's negative infinity to infinity. The limit is x goes towards negative infinity, so as our x's go to the left, our graph is going down, and it's going to keep going down to negative infinity. As we go to the right, our graph is going to keep going up, and so therefore it's going to keep going up to positive infinity. So the limit is x approaches positive infinity, f of x equals infinity. We have x and y intercepts again at 0, 0. All right, and then what else can we talk about on this? So let's see, increasing, decreasing. Well, our graph is increasing the whole time. Now, right here in the middle, it starts to slow down, but it's still increasing, okay? So we can say that it's increasing from negative infinity to infinity. Symmetry. This graph is odd. It's symmetric to the origin. It's not bounded. There's no local extrema, no asymptotes. In behavior we talked about. And is it continuous? It is continuous. All right, moving on. The next one it talks about is the square root function. And so that's f of x equals the square root of x. Now this is one of them that when I go to graph it, I have to change my table a little bit because we're dealing with real numbers in our graph, so we're not going to have any imaginary numbers. And I know that we can't take the square root of a negative number, so my table is going to start at 0. I also want to pick numbers that are nice, have nice pretty square roots because we don't want to deal with decimals. So 1 has a square root, 2 doesn't have a nice pretty one, 3, nope, 4, 5, 6, 7, 8, and 9 has a pretty one. So we're going to take the square root of those numbers. The square root of 0 is 0, square root of 1 is 1, 4 is 2, square root of 9 is 3. And so we can plot them. And so our graph will only keep going to the, whoops, I missed that, to the right. Because if we go to the left, we're going to have negative x's, and we said we don't want them. All right, so let's see. Our domain, does it keep going to the left? It does not. But the furthest point to the left is at x equals 0. Does it keep going to the right? It does. No gaps, no holes, no jumps. So therefore, it's going to be from 0, which is included, to positive infinity. Does my graph keep going down? It does not. The lowest y value is at 0, where y equals 0. But it does keep going up, okay? It's what they call increasing at a decreasing rate. We're still going up. We're just going up slower and slower each time. So therefore, my range is going to start at the 0, and it's also going to go up to positive infinity. Now my limit, as x, notice they changed it, as x goes towards 0, okay, because it's not going to keep going to negative infinity. As x goes towards 0, what's happening to that y value? Well, as it's going towards x is 0, the y is going towards 0 as well, because it has that ordered pair 0, 0. Then the limit as x goes towards positive infinity. So on the right side here, we said we're going to keep going up. We're just going up at a slower rate. So it is going to keep going up to positive infinity. Our x-intercepts, well, again, we have x and y-intercepts at 0, 0. And then some other stuff. So let's see, we can say domain, range, roots, y-intercept, just reading through our list. Increasing and decreasing. It is increasing. and it's increasing from 0 to infinity. It has no symmetry. It's not even nor odd. Let's see, no local extrema. We don't say that it's bounded. No asymptotes. We talked about end behavior. And is it continuous? It is continuous. I can draw the whole graph without picking up my pencil. All right, I'm going to have to stop here for part 1, and then we'll pick up with part 2 in the next video.